At the end of the lesson, you are expected to identify deep feed-forward networks, expound the concept of deep feed-forward networks, and appreciate the significance of deep feed-forward networks. Okay, this lesson is actually the start of something more interesting in the future because we're going to deep dive into the different deep learning algorithms, right? So we're going to talk about the deep feed-forward networks. So what is this all about? What are the different things that we have to always remember about these deep feed-forward networks? So first and foremost, deep feed-forward networks is called the feed-forward neural networks, or it is also called the multi-layer perceptron. So as we go along with our discussions, we're going to learn why it is called multi-layer, feed-forward, and neural, and then networks. All right. So before we continue, please hit that subscribe button to enjoy more our deep learning, mastering machine learning algorithm, and natural language processing courses. So first, let me tell you that the goal of feed-forward neural networks is to have an approximation of the function of the convolution of f. So let me write here so that you would not be able to forget this. So approximate some function of, we have the convolution of x, okay, or the function of some convolutions of f, right? So we have here our example. We have y equals to the convolution of f and x. What does this mean? So if you could still remember in our lesson, so we talked about mapping, remember? So don't forget that lesson because it has something to do always with what we're going to talk this time and of course in our future lessons. So what does this one mean? So it means that we have here an x, which is an input, and if we're going to input the value, any value of x, then it will give us a certain value of y. Okay, so that means when we are going to map this one, so okay, it gives us the some values of y. Okay, so this means that for any given value of x, this will always approximate to any value of y. Of course, when x has different values, then y would have different values too. So feed-forward networks defines this kind of representation. And maybe you would like to ask me, are we not going to include some forms of parameters that we have in our past lessons, or even when we connect this lesson to machine learning when we define a model? So is having a parameter not included in this kind of type? The answer is no, because in mapping some parameters, or in mapping different functions, we also have to include the different parameters. So for example, when we say y is equal to, this is f, okay, f, the function of f having the parameters theta. Okay, so when we have this kind of statement, what does this mean? How does the feed-forward neural network behave in this way? So it means that the feed-forward neural networks defines the different values of y with respect to the given value of x having the parameter theta in this case. So this would result to the best function approximation because we already have here a certain parameter, and this parameter here lets our function learns the different values. So we have here different terms, the feed forward, the neural networks. Of course, we have here multi-layer perceptrons, but as of the moment, we're going to focus on the feed-forward neural networks. The first question is that, why is it called the feed-forward? I think that's a very nice question. So it is called feed-forward because the function is evaluated, or the information is evaluated having passed through the different points in X. And of course, when it is in X, it is evaluated properly. And of course, when there could be different points of evaluation, then we could say that there are so many points of computations. So what do I mean by this? Say, for example, we have F1, then we have F2, then we have F3. Okay, what is the meaning of this? Then we have here X, and then we have here Y, right? This is X, right? So as you could see here, we have F1, we have F2, F3. So these three F's here represent the different layers, okay? And each one has its own characteristics, for example. So that means before you go to Y, or before we get the value of Y, we first have to evaluate the different values of X, considering that we have the different layers here. So first and foremost, we first have to evaluate F1. Then after F1 is evaluated, the information is passed through F2, and then it is again evaluated, thinking the fact that F2 is incorporated, and then F3 is also evaluated when the information coming from F1 and F2 are passed to F3. And then when everything is already evaluated, then we could get the value of Y. So now, in this case, computation really matters. Why? Because for each layer, we have to compute the different values. Remember that F1 is one category of attributes, and F2 is again another category of attributes, and then F3 is also another category of attributes. So as you could see, any input we put into X, it is still evaluated using a different attributes. F1, F2, F1, F2, and then we have F number 3. So feed forward, it's because the information is passed through the different layers. So again, in this case here, we have here 3 layers, F1, F2, and F3. And mind you guys, in feed forward, we do not return the output to X to be tested again. We do not do that, okay? Because the name here is feed forward, so we do not do backward. And in case when we give the feedback to X, then we call that recurrent, okay? Recurrent neural networks. Okay, so the word here is recurrence because it's just like a cycle. We just input again the value of Y to X to pass through again the different layers. Okay, and now let's go to the word networks. I think the word network is already familiar to every one of you guys. It's because this word is really very common. So when we say network, it has something to do with the different interconnections, right? So for example, when we have our telephone lines, then when we say network of lines, then we could imagine, we could picture out the different interconnections of the different telephone lines. So in deep learning, networks also has the same image. It has the same picture because it is composed of different lines or layers having different functions. If you could still remember our topic about the directed acyclic graph, so this one is really very connected to that. And actually, this is really the acyclic graph or the directed acyclic graph if we're talking about directed, right? So let's go back to this one, the F1, F2, and F3. So for example, we have F1, then it goes to F2 here, sorry, then it goes to F3 to make Y. So this is the sequence. This is the direction. As you could see, we could see here the arrow which points out the direction from one point to another. So F1 is connected to F2 and F2 is connected to F3, and then we have here the last point, which is Y. So we do not do F1 to F3 because it would mean a very different case. The output could be different if we do that. That's why it is called acyclic directed. As you could see in here, our outcome or our function is composed together, and they are connected by the different points. So it is just like a chain. For Y to be resulted to, F1 has to be connected first to F2, and F2 has to be connected first to F3. So we could not see here any shortcuts. Having shown you this one, then we could say that F1 is actually the first layer, the F2 is the third layer, and our final layer is actually Y, and F3 is our third layer. The most interesting about each layer is that its nature, its width or length, is dependent on how many attributes it contains. So for example, F1 can have 1, 2, 3, or 4 attributes. So for example, if we're talking here about sales performance, for example, then we can have person's age or the customer's age, income, social status, education, and many more. So there could be a lot of things that goes on with F1. And the same is true with F2, and also the same is true with F3. And the most interesting part of this one is that how are we going to arrive at a certain value of Y? What do we do with a certain value of X? Of course, in this case, what we do here is we match. Okay? So for every function of X, we match that to the convolution of X and F, right? So that means for each X, we always think that it is always related to or accompanied by a certain name tag, which is Y, is always approximate to the convolution of X and F. And because we said that in every layer there is always a computation involved, so for example in this case F1, F2, and F3, we first have to deal with F1, and then for each layer we have to always produce a certain value that could match a certain value of Y. And maybe at this point you would like to ask me, is it always that for every training point do we always think that a certain layer has a certain value? So for example, F1 has a value to at least correspond to a certain value of Y. If not really correspond, but at least it must be closer to a certain value of y. Would it mean that f2 and f3 would always have a certain value? Of course, the answer is not. Okay, so it is not always that the values of certain layers are specified. And why is that? So if the values of some layers are not specified, does it mean that the training data, our model, is affected as to its performance, as to its outcome? What then would the learning algorithm do? So in this case, what our learning algorithm must do is that it has to choose whether or not to use certain values of f2 and f3 for it to have arrived at a certain value. So in short, it has something to do with the manner of choosing the values of f2 and f3 for it to arrive at a certain value of y. But the good thing about this one is that our training data does not dictate the layers what to do, or it does not tell f2 and f3 which of these values or what value they're going to tell the training data to use. So this means that the very function of f2 and f3 in this case, as far as our learning algorithm is concerned, is that it has to just wait for the learning algorithm to tell them how to use its features, its values, so that it can best implement the approximation of fx. Why is it called neural? Okay, so basically it's called neurals because it is inspired by neuroscience, and neuroscience, it has something to do with the study of our brain, human brain to be more specific. Let me write that, neuroscience. Just like our brain, the neural network is interconnected, and there are so many layers. And we've said just a while ago that the dimensionality of each layer is determined by the width, or determines the width of the model. So that means the more attributes each layer contains, the model is more wider. So what this means is that each unit is like a neuron, and this neuron receives lots of outputs of information from different neurons, just like what we have a while ago. So f2 receives information from f1, f3 receives information from f2, and from f1 through f2. So because we are talking here of the different values that are passed through from the different layers, so we always have to think that there is always a vector to scalar function for each layer, or vector to vector function for each one of them. So this is actually a concept of neuroscience, and time has taught us that it's not actually that easy to always think our network as really the same as human brain. It's because that would be difficult to do. So the modern approach to neural networks is now guided by many mathematical and engineering disciplines, because our goal is not actually to perfectly model the brain, but at least to make the functions of the brain our inspiration to understand how everything really works. What is this for? Why do we have to study this? Having a proper understanding of deep forward networks can help us better understand deep learning algorithms, which we will have one by one as we go along in this course. It is also very important to machine learning practitioners, because this provides them the foundations to many commercial applications. It's like, for example, convolutional network is used for object recognition. After all being said and done, let's try this. What is deep feedforward networks? How does deep feedforward networks work? Why do we have to understand deep feedforward networks? Please leave your answers in the comment below so that we would be able to have a very rich interaction of ideas, and we can learn from each other. Do you want to know more about this course? Just click the card on your right screen. You can enjoy our deep learning, mastering machine learning algorithm, and natural language processing courses. Learn and upskill for free.